In a kind and gentle universe, we're always given frequency tables with carefully labeled rows and columns. We don't live in that universe. We often have to construct our own tables. The most useful tables have cells that allow every possible outcome to be categorized, cells that correspond to mutually exclusive events, and total amounts. For example, suppose that at a party a person could have cake or ice cream. If there are 37 servings of cake and 25 servings of ice cream, then there were 62 people at the party. Or were there? Remember, if you don't find your mistake, someone else will. A person could have cake or ice cream, but it's also possible they had neither. And remember that, to a mathematician, or is inclusive. So a person could have both. For example, let C be those who got cake and I be those who got ice cream. Then we have four possibilities. Someone got cake but not ice cream, C intersect I complement. Someone got ice cream but not cake, C complement intersect I. Someone got both cake and ice cream, C intersect I. And someone did not get cake and did not get ice cream. So we could create a table with four cells, but we won't. Instead, we can organize the same information into a two-way table. The row labels correspond to one set of events. The column labels correspond to another set of events. A cell corresponds to the intersection of the row event with the column event. As with other frequency tables, we want to be sure that the cells correspond to mutually exclusive events and all outcomes appear in some cell. So a badly organized table might look like this, since not all outcomes can be placed in a cell. For example, C intersect I is not at the intersection of any row or any column. If we just have two events, one event and its complement can be the row label, and the other event and its complement can be the column label. Now, any combination of the events C and I and their complements correspond to a cell entry. We can populate the cells with the number of occurrences, and assuming we have the data, our table might look something like this. And we see that this ice cream row tells us there are 25 people who had ice cream. In addition to these people, there are 26 other people who had cake. And so there's a total of 51 persons who had ice cream or cake. Now remember an important strategy. Solve it again. If we only knew that 37 persons had cake and 25 had ice cream, we'd know the row and column totals, and our sum would actually just be too much. And that's because it counts these 11 people who had both ice cream and cake twice. Once as a person who had ice cream, and a second time as a person who had cake. And that means we can get the correct count by removing the duplicates. And so we can do the computation 37 plus 25, those are the row and column totals, minus the 11 that are common to both, and that gives us the same answer, 51. Now, when we have to choose between a choice and its complement, we have what's known as a binary choice. You have cake, or you don't have cake. But there are many cases where, while we still have to choose one and only one thing, we have more than two choices. We say these are non-binary choices. We can organize these into a table as well, provided we remember all possibilities correspond to a cell, and cells have to correspond to mutually exclusive events. For example, in an emergency room, a patient's condition is categorized as stable, serious, or critical, and some patients die. Now, a patient's condition can't be categorized in two ways, so we can let stable, serious, and critical be the column labels. They could also be the row labels. And a patient either dies or does not die, so we can let these be the row labels. And we should also include the totals. And so our table might look something like this, and filling in the tabulated data, we may get something like this.